So, an interesting relative motion problem here. Now, we've done a lot of these block and pulley problems before, but in this case, we've got a pulley that moves, and that's going to mean that these two masses don't have the same acceleration. Sorry. So, for instance, if this mass falls a centimeter, that means the pulley goes down a centimeter. That means you need a centimeter more of string on this side and on this side. That means this mass has actually moved 2 centimeters. So that if this one's accelerating at rate a, this one will actually have an acceleration that is twice as much. Another way to approach that is to use constraint. And the constraint that will be used is the length of the string. So let's call this distance S1 measured from this fixed point here, and this distance S2 measured from this fixed point, because this pulley doesn't move. It's just this one that moves. So this is the distance S2. So then we'll write an equation for the length of the string. Okay, so the length will be S1 plus, then it's got to wrap around that pulley a little bit. So this is just a graphic. Then we have length S2, and then we wrap around this pulley. And again, this is just a graphic to show that length. And then we again have the length S2 on the way back up. And then from there to there, there's another length. Now, key is that the length of the string is constant, as are these three little connectors. So that means if we were to do a derivative, it's going to be 0. So the length of the string is L. That's what L is. It's string length. And it's not changing, so it has a 0 derivative. And so S1's changing, so it has a derivative. But these fixed pieces don't have a derivative, so they're all 0. And you could see we're going to get 2 derivatives of S2 with respect to t. But of course, the derivative of S1, that's just the speed of the first mass. And the derivative of S2, that's how quickly this mass and pulley are moving. So we showed there's a 2-to-1 ratio with velocities. If we were to do a second derivative, and remember a time derivative is L dot, so if we were to do L double dot, well, it's still 0, and that will be the second time derivative of S1 plus 2 times the second time derivative of S2. And the second derivative of position is the acceleration. So you see, once again, a 2-to-1 ratio of the accelerations, as we indicated earlier. A third way that you could obtain that ratio is to use the following idea. The tension in this string will be taken to be constant, and it's this string that pulls up on the left side of the pulley and also the right side of the pulley. So for this little pulley, it's being pulled upwards by tension T and by tension T, and then it's being pulled downwards by this other string connected to M2. Now, if this pulley is taken to be light and has no mass, then when we do net force as ma, because the mass is 0, the net force would consequently need to be 0. And that would mean that the tension force in the lower string would be 2t to balance the forces. So, just use a different color there, twice t. Now, so what this really does is it amplifies the force. And there's a rule known as the conservation of energy that says if you double the force, you have to cut the displacement in half, or the distance in half. So with twice the tension, we get half the distance traveled. And therefore, because distance and acceleration are proportional to each other, so it's half the acceleration. So if this has acceleration a, then this will be half as much, a over 2. So you see the acceleration ratio is just the reciprocal of the tension ratio. And this is really just a statement of conservation of energy. It's conservation of energy applied to machines, because machines that amplify the force, you have to travel a lot more distance with that machine. So let's try a typical problem here. So here we've got a block and pulley system. Here's a moving pulley, and we will relate the accelerations of these two masses. First of all, if this string had tension T, then it's wrapping around here still with tension T, and around here still with tension T. So there's a tension T pulling up on this mass. But here with T and T here, this will be twice T in this string. And therefore, if this mass has acceleration A, with twice the tension in this chord, there will be half the acceleration there. Now, if we instead tried to do that using the other valid technique, which is the string length constraint, so we would see that so we've got a fixed length of string, then there's a certain distance, I guess we'll call it S1 to right there, and then a fixed length, and then S1 again. This is a fixed point right here, right? This reference location, this isn't moving. And then we'll define another distance, S2, which will be from that fixed point down to here. Okay, now S1 and S2 are going to change as the system moves, but the length of the string doesn't change, so let's write an equation for the length of the string. So we got a fixed length, and as we saw in the previous page, we could just ignore that. Then we have a distance S1. Fixed length around the pulley, we can ignore that. Then again, S1. And then we have this distance on this side, S2, plus another fixed length. So that if we do a derivative, string length is constant, so its derivative is 0. We could see a relationship between the velocities. If we do another derivative, then we'll get a relationship between the second derivatives, which are the accelerations. And again, we can see that the acceleration of mass 1 is going to be half the acceleration of mass 2, which is exactly, the acceleration of this mass is going to be half the acceleration of this mass. So it's an A/2A ratio, exactly as we showed before. Let's try that again. All right, so here's another block and pulley system. So let's say this was tension T. The string wraps around there. So it's pulling up on this lower pulley with tension T here. The string wraps around and is also pulling up on this side with tension T. Then wraps over this pulley, and again is pulling up with tension T at this point. So you actually have T, you actually have 3 times T then in this string. And that means ratios, if this is acceleration A, this should be acceleration A over 3. We can verify that using the string length constraint. So we'll measure distances from here because this is a fixed length. And so this will be distance S1. And then for this mass, we'll measure from this point here. That's a fixed length, and that will be distance 2. And so we'll just write an equation for the length of the string. So here's our first fixed point, and here's our second one. That's our origin. Okay, so length of the string. So starting here, we're going to have S1, S1, a fixed length, and then S1 again. So we'll define this as being distance 1. This is distance 2. So we got S1, fixed length, S1, a fixed length, and S1. So that's 3 S1s plus a fixed length, a fixed length, a fixed length, and S2. So doing a first derivative, the string length itself isn't 0, it's a constant, I should say. Just getting too excited there, but its derivative therefore will be 0. So time derivatives can be written in dot notation. Second derivative of position is acceleration. So we see that the first acceleration, the acceleration of this mass over here, this pulley and mass together, is going to be a third of the acceleration of this mass, which is what we said above. Now you may wonder about this minus sign. It just means that if S1 is increasing, then S2 clearly will be decreasing. So there's an opposite direction there in a sense. Now, this technique is general and will work everywhere. That sort of tension ratio technique won't work in this following question. Here we just have one string, so that if the tension is T here, then it's still T over here. The way this problem works, though, that if you move this string a centimeter, then it's true we've got a centimeter less on this side, but the cart is actually going to move a distance that's different from a centimeter. So it's a little complicated, and that simple tension ratio technique won't work. The technique of writing an equation for the length of the string will, however, work quite nicely. So there's two contributions to the length of the string. There's this sort of hypotenuse bit here, and then there's this little bit here that wraps around the pulley. So we'll introduce another variable. We'll call this height here y, and we see we have a distance x already here. So this hypotenuse bit is just the root of x squared plus 15 squared. And then this little bit here, this y distance, will be 15, or sorry, the length of the string will be 15 minus the y coordinate. So there's an equation for the length of the string. Now that is a constant, so if we do its time derivative, dl dt, I'll remind you that's what dot notation means, that will be 0. Now, the derivative of a square root function, well, let's just use a little space that we have up here. So if you've got root u and you're doing its derivative, so this is u to the 1/2, so that's half u to the minus half. But then you have to multiply by the derivative of the inside. Now we're actually doing time derivatives here, but it's going to work the same way. The time derivative of this is going to be 1 over 2 times the square root, and the stuff inside the square root isn't changing, so I'm just going to leave it like that. But then you have to multiply by the time derivative of inside the square root. So the time derivative of this is going to be 2 times x times the time derivative of x dot. And then you do the time derivative of this, and it's just minus y dot. So we're not in Kansas anymore, Dorothy. This is clearly a little complicated and interesting. So you bring the y dot over here, and then you cancel the 2's here. And the thing inside the square root is still the same, not changing. So y dot, well, y, that's the rate at which the string is getting closer to the ground, so it's the speed of the string. And x dot, well, that's the speed of the cart. And so clearly they're not the same because there's this term here, x over the root of x squared plus 225 between them. Now, we were asked to connect the accelerations. That means we have to do a second derivative. So we could just do the ddt of this thing. It's a little complicated because you've got x over the square root. Okay, I'll put back in here what was inside the square root. So there's 3 things, the x dot, and the square root. So I'll treat this as a product rule where this is one term and this is the other. So we'll leave the first term alone and multiply by the time derivative of the second term, so that'll be x double dot. Then we'll leave the first term alone, and then we've got to multiply by the time derivative of this. We will use the quotient rule for that. So square the denominator, take the denominator and multiply by the derivative of the top, minus the top times the derivative of the bottom. Oh mon Dieu. Okay, so that's going to be 1 over 2 times the square root times the time derivative of the inside, and that's going to be 2x dot. Oh my goodness. So clearly this is complicated. There's a complicated relationship between these accelerations. So the acceleration of the string is proportional to the acceleration of the cart, and then it's actually proportional to the speed of the cart as well. So x dot's the speed of the cart squared, and then we get square root over square root squared, so that's just over square root. And then our final term here, we'll have to do some simplifying here. So we're going to get x dot squared, and here we're going to get x squared. The 2 will cancel out, and then we'll end over this thing, square root thing, x squared plus 225 cubed. And so it's x squared, x dot squared. So a simple looking little problem ends up having a really interesting complex physics. But the point is that the technique of writing out an equation for the length of the string and differentiating it twice gives us the answer that we're looking for. All right, so now where are we going to use these things? Well, dynamics problems. So let's get back to a nice old dynamics problem. You know, lots of familiar stuff here, bullet blocks and pulleys, inclined plane, frictionless inclined plane, but then this moving pulley, which is what separates this from, say, analysis that you would have done before in Physics 12. So we start with forces. Okay, there's 8 G's of weight, there's a normal force, there's a tension in the string. So then we write F equals ma on that mass. For this one, there's just weight, and then there's a tension. Now, if we do our analysis there, we would say, okay, if this is tension T, then this will be T, this will be T, this will be twice T, and this mass will have half the acceleration downwards that this mass does down the ramp. Okay, so we've got the weight, m times g. G is 9.81. Here's 8g. This is normal force. Now, we will need to resolve this force into its components, right? There'll be an 8g cosine 20 and an 8g sine 20. That's the force that actually pulls you down the ramp. And just a reminder that it is sine because it's the opposite side of the triangle. This angle's 20, this will be 70, this again will be 20, always the same as the ramp angle. So it's the opposite side, it's pulling you down the ramp, and it's 8g sine 20, and I'm just trying to put it back where I had it because that's where I like it. Okay, so now we write out the force equations. So we are getting in now two dynamics, F equals ma. We've been focusing thus far exclusively on the statics problem, but now it's time for some dynamics. So putting our x-axis down the ramp, we'll have 8g sine of 20 plus tension being the net force on the 8 kilogram mass. And putting our x-axis straight down on this mass, there will be 4g minus twice t equaling 4 times its acceleration, which is half a. So here we have a system, two unknowns, tension and acceleration. We'll solve it. Now, typically with these problems, you could use elimination directly, but here, because of that moving pulley, we'll have to do a tiny bit of linear algebra here. It's pretty simple. We're just going to double the first equation and add it to the second. Sorry, that's wrong. So 2r1 plus r2. The reason we double the first equation is that then you have 2t, and then that will disappear with the minus 2t. So it'll be 16g sine of 20 plus 2t, and then you add on to that 4g minus 2t, and so that wipes out. On the other side, we've got to remember that we're doubling this first equation, so that'll be 16a, and we're not doing anything to the second equation, so when we add it, it's still twice a. And so solving for acceleration, it's just 16g sine of 20 plus 4g over 8t. All right, so that's a relatively straightforward problem. Just a slight extension of what you would have done in Physics 11 and Physics 12. Now, it's important that we're able to do a bit of reasoning to figure out which way these systems are going to go. In the previous problem, it was obvious. Both of the masses were going to drop. But here, if the 10 kilogram were to drop, then the 6 kilogram would go up. So these are going to have opposite senses for their accelerations. And it's not immediately clear, because of the doubling of the string here, which way this system will go. So we do need to be able to use a bit of reasoning. So what reasoning do we use? Well, we know if this tension's T, it's going to wrap around there, pull up on both sides of the pulley with tension T. So that means the tension in this cord, assuming a massless pulley, will be twice T. So if this system were at rest, then the tension, if we focus on this mass, would equal the weight of that mass, 6g. That would mean over here that you would actually have 2 times 6g. You would have 12g pulling up on that mass. Just draw the picture right there. 2 times 6g is 12g. Well, clearly that tension then exceeds the weight of this 10 kilogram mass, and so it would not be in equilibrium at all. It would be tending to go up. Now, if that argument suffices to tell us that this mass is actually going up and this mass is going down. So I'll say this is like argument A. Or if you want, you could also make argument B to get a consistent solution. If this mass were at rest, then, cross that out, twice T would equal the weight of that 10 kg mass. So that would mean a tension of 5g. And if we came over here, if we were looking at the 6 kilogram, there would only be 5g of tension, and clearly this wouldn't be in equilibrium. It would be tending to go down. So we see both of these ways of thinking consistently tell us that the 10 kilogram is going to tend to go up and the 5 kilogram is going to tend to go down. Now, the tension is not actually either of those values. It actually turns out to be somewhere in between. However, the 10 still goes up and the 6 still goes down. So this bit of reasoning enables us to determine the direction the system's going to go, and therefore to write proper force equations straight out of the gate. So what did we just find? We just found that this mass is going to tend to go up, and this mass is going to tend to go down. Now, we also, you'll recall, worked through here and said this was twice t, so this acceleration is actually going to be half a. And this will be acceleration a. So we'll finish the force diagram. So the tension 2t is pulling up on this mass, and clearly we'll have 10 g's of weight down. This has tension T pulling up, and 6 g's of weight going down. So now we'll write net force equations. So we'll point our x-axis in the direction of the acceleration. So our x-axis is going upwards here. The mass is 10. Its acceleration is half a, as we reasoned. This mass is accelerating down, so we'll point the x-axis, the positive axis, downwards. To solve these equations, we'll double the second one, because that will then enable us to cancel out the tension term. So doubling this equation gives us 12g. Adding to the first equation, we can see that the tension part will cancel out. So doubling the second equation will give us 12a. Adding to the first equation will give us another 5a. So solving for acceleration, we get 2g over 12 plus 5 over 17. Here's a task for you now. Pause the video and do 3 things. First of all, relate the accelerations between these two masses. If this one's accelerating at rate a, what's the acceleration of this mass? You can use the string ratio technique. Then figure out which way it's going to go, So if you held this mass at rest, what would be happening to this one? Finally, write force equations and show that the acceleration is 3g over 29, where if g doesn't mean gram, of course, it means 9.81 newtons per kilogram. So pause the video, give this one a try, and then watch my sketch solution that will follow. Okay, so if this was tension T, then you'd have TTT, you'd have 3T pulling up on this pulley, so this tension has been tripled in the supporting string. That means if this is acceleration A, this would be A over 3. Notice that in the force equations, 8A, 15A over 3, I put in that acceleration expression there. We need to think about which way it goes. So if this mass were held at rest, then 3T would be equal 15G. If that was the case, then the tension would be 5G. Now we've got to compare that over here with the force pulling you down the ramp. If that's 8G sine of 30. Sine of 30 is a half, so this is 4G's of force down the ramp, 5G's of force up the ramp. This force wins. This mass is going to move up the ramp. You could work the reasoning the other way and say the tension is 4G, come over here and find out that you don't have enough to support this mass, so it's going to accelerate down. From that point, you write the force equations, you triple the first equation, add it to the second, and then you arrive at the desired result. The acceleration is 15 minus 12 is 3G over 29. And that's a look at a relative motion problem of interest.